Hey everyone, and welcome to This Explainer. Today, we are diving headfirst into the architecture of artificial intelligence. If you follow the tech space at all, you already know that the era of deterministic, rigidly coded software is pretty much over. We've rapidly transitioned into this wild new era of non-deterministic, probabilistic models. But instead of just looking at what these systems can do, we're actually going to pop the hood. We're going to explore the precise structural mechanics operating right beneath the surface. We'll examine the specific framework of algorithms, parameter optimization, and neural architecture that literally makes modern AI possible.
Which really brings us to the big question, right? What is the actual architecture behind artificial intelligence? Because, once you strip away the slick user interfaces and all that flashy product marketing, how do these complex layers actually interact? We're talking about the massive leap from raw data processing into high-dimensional vector spaces and deep neural networks. Getting a grip on how these highly technical components are structurally organized is absolutely crucial for understanding where this tech sits right now, and maybe more importantly, where its limits are. So today, we're breaking down exactly how those underlying mechanics function together to power the systems we use every single day.
All right, here is our roadmap for today. Number 1, AI basics and core concepts. Number 2, decoding key AI terminology. Number 3, AI in everyday life. And finally, number 4, AI impact across industries. Let's get into it.
Section 1, AI Basics and Core Concepts, the broad view.
At its absolute most fundamental level, the framework of AI represents a massive paradigm shift. We're moving away from rigid, rules-based logic and diving into statistical pattern recognition. Instead of software engineers sitting down and manually typing out every possible if-then scenario for a program to follow, AI creates systems that can reason through mountains of data to independently optimize for a goal. The whole core concept here is about mimicking cognitive perception, but doing it within a high-dimensional mathematical space. The machine takes in inputs from its environment, processes that data to find correlations that are honestly completely invisible to human analysts, and then takes action. It's the grand idea of building computational models that don't just blindly follow commands, but actively adapt and optimize themselves based on the data they eat.
Moving on to Section 2, decoding key AI terminology, the microview.
To really understand how this adaptation happens, we've got to separate the big picture from the actual engine driving it. Think of artificial intelligence as this giant overarching umbrella. It's the destination, right? The general capability of a system to act intelligently. Machine learning, on the flip side, is the specific vehicle that gets us there. It's the tactical, boots-on-the-ground application of statistical methods that let these systems automatically learn and improve from experience without explicitly being programmed to do so. Separating the broad theoretical goal of AI from the deeply mathematical, data-driven mechanics of machine learning is absolutely key if you want to understand how these modern systems are engineered.
Let's look a little closer at that engine. Machine learning revolves entirely around minimizing error. When you train a machine learning model, it's essentially tweaking millions or even billions of internal parameters to perfectly map an input to an output. Usually this happens through processes like gradient descent. The system actively calculates what we call a loss function, which is basically just a fancy measure of how wrong its current predictions are. And then it continuously updates its parameters to shrink that loss down over time. It is a brutal, rigorous process of iterative optimization. So instead of a programmer hard-coding, hey, this is what a cat looks like, the system analyzes thousands of pixel patterns and statistically figures out the defining features of a cat completely on its own.
Now, inside the world of machine learning, the absolute heavy lifter for handling super complex nonlinear data is the neural network. Picture it like a layered cake. You've got an input layer, a bunch of hidden layers in the middle, and an output layer. Inside those hidden layers are artificial neurons or nodes. When data flows through, each node takes the input, multiplies it by a specific weight, adds a bias, and then fires that result through an activation function, like a ReLU function, to decide if the signal should keep moving to the next layer. It's this incredibly complex web of weighted connections that allows the network to capture totally subtle, nonlinear relationships in the data. It breaks complex things down into math vectors to arrive at a highly accurate probabilistic guess.
But what's actually pulling the strings of all these networks and models? Algorithms. And we aren't just talking about basic sorting functions you'd learn in a beginner coding class. In modern AI architecture, we are dealing with highly advanced algorithmic structures, like the self-attention mechanisms you'd find in a transformer model. These sophisticated algorithms are basically the underlying physics engine of the network. They allow a model to dynamically figure out the contextual importance of different pieces of data all at once, rather than reading things in a rigid step-by-step order. This precise algorithmic logic dictates exactly how the neural network updates its weights, processes context, and ultimately optimizes everything to spit out a meaningful result.
Section 3. AI in everyday life. Zooming back out.
All right, let's step back from all the parameter optimization and loss functions for a second. Let's look at how these microscopic mechanics seamlessly blend into your everyday life. Take the smartphone sitting in your pocket right now. Modern computational photography isn't just about letting light hit a lens anymore. It's using edge computing and neural networks to perform semantic segmentation on the fly. It instantly identifies what's in the foreground, what's in the background, and applies distinct pixel-level lighting adjustments in literally milliseconds. Or think about your phone's battery management. It continuously runs behavioral models via machine learning to optimize power drain based on your specific habits. This insanely intense mathematical architecture is just humming along continuously in the background of our lives.
And that brings us to Section 4, AI impact across industries, the global scope.
Now, take that exact same underlying architecture we just talked about and scale it up exponentially to global industries. The impact is staggering. In healthcare, convolutional neural networks are aggressively outperforming traditional methods. They are segmenting MRI scans at the pixel level to spot microtumors way before a human doctor could ever see them. Over in the financial sector, unsupervised anomaly detection algorithms aren't just looking at where a credit card transaction happened, they are actively analyzing behavioral biometrics. They look at the micropatterns of how you type on a keyboard or swipe on your screen to catch fraud in real time. Because this foundational architecture relies entirely on math and data, rather than hard-coded rules, it has near infinite scalability to completely revolutionize these massive global workflows.
So, we've covered a lot of ground today. We explored the shift from rigid code to probabilistic models, broke down machine learning engines, diving into the dense vector spaces of neural networks and the complex algorithms driving it all. But honestly, as compute power explodes and these systems scale from billions to literally trillions of parameters, we are only just beginning to see what this architecture can do. So I want to leave you with this thought. As these deep learning architectures become even more optimized, how will this exponential jump in processing power fundamentally alter the limits of our entire world? The foundation is built, for sure, but its ultimate ceiling, that is still entirely unknown. Thank you so much for joining me on this explainer, and I'll see you next time.